Horizon just UX, and this is the insane engineering of the F-16 by the child Real Engineering. Yes, this is an F-16 video, was just posted a month ago, which is awesome because it's the one video I haven't done is about F-16s basically. Because I always assume F-16s are just like F-15s but with one less engine. But apparently that's not the case. And I'm pretty sure I got a feeling from one of the comments that it was developed a bit differently. I don't know. But F-16 is like one of the, apart from F-22 I guess, F-16 is one of the best dogfighting vehicles for decades now, right? F-15 being the more powerful one, right? F-15 is dogfighting, F-16 is dogfighting, but F-16 is like more nimble one. It's more effective that way. F-22 is even better than that, apparently. I don't know. But it's going to be, F-16 is basically just like all-time great type of thing, right? Hall of Fame. So I've never watched a video about this, but it's going to be interesting. I'm pretty sure I also saw a video, it was from the Real Engineering, right? F-35 video that showed F-16 for a bit, and I'm like, wait a minute, that looks completely different than F-15. Having the, that air intake in below the plane, which is like weird. I've never seen any other plane having something like that, but yeah. So that's really fun. Although anything military, related, I've been in this kind of a rabbit hole for past, week, 2 week, a month, I don't even know the time. But since I started to react to like Federal Attrition, I'm like, whoa, look at this, like, tank, this is good. I guess Federal Attrition has this kind of like charisma to him that can make you invest in things. So it's just like tanks, this, and then planes. I'm like, what the fuck? F-15 video, the SR-17 Blackbird. I'm like, wait a minute, let me check. And they're like task and purpose, now Real Engineering, mustard. I've been through this rabbit hole, and there's still way too many videos that I haven't even touched and don't even know about it. But I always heard about it, all these equipments, which is like, okay, this is going to be interesting watching. So yeah, if you want to react to any more videos, specifically comment down and subscribe. Basically, if you want to keep up to date what I'm going to react in the future as well. And yeah, let's watch it.
This video is brought to you by Nebula. Watch our bonus videos with F-16 test pilot David Kern by signing up to Nebula for only $250 a month. A fully loaded F-16 is a force to be reckoned with. An air superiority machine that countries the world over use to patrol their skies. A low-cost, lightweight, single-engined fighter specifically designed to outmaneuver its opponents while carrying state-of-the-art missiles that would, hopefully, mean it would never have to. The F-16 was born out of the Vietnam War. Large, heavy, complex US fighters like the F-4 Phantom were the norm, but the F-4 found itself in peril frequently, at a significant disadvantage when taking on the smaller, maneuverable Soviet-made MiGs of the Vietnamese Air Force, like the MiG-21. The MiG-21 was a small, single-engined, lightweight aircraft with thin delta wings. The F-4 was fast, flying up to Mach 2.2, traveled further, and carried more missiles, with a powerful radar. But its lack of maneuverability at low speed, poor pilot visibility, and easy identification due to jet engines that billowed black smoke trails made it vulnerable to sneak attacks from the Soviet interceptor. MiG-21s frequently flew close to the ground.
What? A plane basically puts smoke like that today would be like a death sentence instantly.
Under radar and ambushed incoming F-4s, making a single attacking run with their ATOL infrared guided missiles, and then using their low-speed maneuverability to outturn and escape. From August 1967 to February 1968, US losses in Vietnam were staggering, losing 18 aircraft while downing just 5. For a nation accustomed to absolute air superiority, something was off. The MiG-21's introduction in 1966 forced the US to adapt. Its large heavy fighter bombers, while useful, were at a disadvantage against these smaller, cheaper planes, and something needed to be done. The Red Barn study, commissioned by the US military, began to identify and address the tactical and technical issues causing the heavy losses that both the US Navy and Air Force were experiencing in the Vietnam War. And their findings led to the development of one of the world's most ubiquitous fighter planes, a plane designed with a new physics-based doctrine at its core. Entering service in 1978 and standing the test of time, it is now confirmed that the aircraft will be entering the battle for Ukraine's freedom, taking on the modern-day counterparts of the MiG. This is the insane engineering of the F-16.
Yeah, one thing I'll learn about Ukraine war is that they have like Sukhoi planes and things like that, right? Sukhoi Su planes, I guess, which is like, okay. So it's weird, like they're using Russian equipment to fight Russia. Like that's some like which is like interesting, right? It's like feels irony a bit in Russian side at least, right? They sold all this equipment to Ukraine, and that's the one they're using to fight against. But also like American ones, like F-16 and things like that. And doesn't that cause issues to the soldiers there basically? So I'm pretty sure there must be style differences between these planes. Like if you're gonna jump from Russian to American like that.
The F-16 was built from the ground up with this classified 1966 paper as its guiding light. A paper full of mathematical models, graphs, and equations designed to answer one question: how to win a close quarters dogfight. Created with the help of military supercomputers, it defined a new concept: energy maneuverability. Created by Colonel John Boyd, an Air Force veteran of the Vietnam War and one of the members of the so-called fighter mafia, with the help of a civilian mathematician, Thomas Christie. These graphs were the basis for defining a plane's maneuverability through its full range of speeds: Mach number on the x-axis, turn rate on the y. A theory underlined by the management of both kinetic and potential energy, speed and altitude. In order to change direction, a fighter aircraft must trade energy from these reservoirs, and doing it as efficiently as possible is the key to outmaneuvering an enemy. This is the energy maneuverability diagram for the F-16. It's a complicated graph to read without some basic understanding. This line is defined by the maximum lift of the aircraft. This is important because it determines the maximum turn rate at a particular speed in this region. We need lift to turn. To begin a turn, an aircraft will roll in the direction of the turn. This splits the lift the plane is generating into two components: a horizontal component that causes the plane to turn, and a vertical component that keeps the plane in the sky. A steeper bank angle will increase the horizontal component and increase our turn rate, while stealing lift from the vertical component. This vertical component needs to equal the weight of the aircraft, or the plane will lose altitude. To compensate for that, the pilot will need to increase lift by increasing the angle of attack. This is where the maximum lift issue arises. More lift means more available force to turn. To determine the max turn rate for an F-16 at 0.4 Mach, we simply draw a line straight up and across to our turn rate, 13 degrees per second. Now this is where things get interesting. This is the graph for an F-4E. At the same speed, the F-4 can make a maximum turn of just 5 degrees per second.
Damn.
To determine a sustained turn, we look to this line labeled with a 0, meaning no loss of altitude is required to make the turn. We can see the F-16's best sustained turn is 14.2 degrees per second at 0.85 Mach at 7G. The F-4's best sustained turn is 10 degrees per second at 0.85 Mach at 5G. This is what that looks like in practice. It takes the F-16 25 seconds to complete a full 360-degree turn, while it takes the F-4 36 seconds, 11 seconds in the difference.
Yeah.
The F-16 was a radical new way of thinking about fighter aircraft, and
Wait a minute. How much of it is like how fast is F-22 in this regard? I'm guessing must be even like faster degrees, right? Making a faster turn. I don't know, 15 seconds or something. I don't know. I don't know how much
that
difference that
design
is.
philosophy can be seen with how the engine inlet has been designed to deal with supersonic flow. To learn more about the F-16, we spoke with an F-16 test pilot.
So the F-16 inlet is one of those things that tells you about the design philosophy of the aircraft. Because up until that point, the thought process was we wanted to go faster, we wanted to go higher. And nobody stopped to ask why. Because it turns out that not a lot of fights, not a lot of air combat was happening in that Mach 2 plus range. In fact, very little of it was happening, and it didn't have a huge amount of tactical application. And so
Humans are fighting, man. Regardless of like, okay, the technology can go up, but humans, I don't know, response and reflexes are not going to go up. Dogfighting at Mach 2 plus is like, imagine that speed, like how fast you need to react to shit. How are you going to do that, right? So I guess it makes sense. Like they just like this, they came with like World War I type propeller planes, which didn't go that high and didn't have that kind of ability. From then, like, let's just increase the speed and height type of thing, like how high can it fly, how fast it can go. But before they reached a cap, like, okay, just now it's like more about maneuverability. Like, we can't just do this shit.
As John Boyd and the rest of the team was looking at this lightweight fighter design, which became the F-16, they said, well, where do we think that the dogfights of the future are really going to happen? And they said, well, it's probably going to be somewhere in that 0.8 Mach to 1.2 Mach regime. That's really where we need to be in terms of optimizing the performance of the jet. And we see that here in terms of the specific excess power chart, where it's got this advantage right here in that range of 0.8 Mach to 1.2 Mach. That's where the fat part of the chart sits. That's where you're fat on energy. That's where you have that advantage. And so the F-16 propulsion system is not optimized to go over Mach 2, although it can. And I've flown the F-16 at Mach 2. You run out of gas pretty quick, but you can go that fast. But in that, what we call transonic regime of 0.8 to 1.2 Mach, you've got a different design problem than some of the previous jets. And you can see that in terms of the inlets. The inlets on the F4 have this extension that goes sort of along the cheeks of the aircraft forward, and then the actual inlets are set back. And what that's designed to do is attach a shock wave to the front of that inlet lip, and then it goes backwards and expands along the body, and that shock wave is basically going to cover up the inlet. That has some thermodynamic effects in terms of pressure recovery for the fan face, because you don't want supersonic air getting all the way in to your turbine. If you have supersonic airflow hitting the front face of that jet engine, the jet engine is going to disintegrate. It's designed to ingest subsonic airflow, and so you have to attach that shock wave at the front of the inlet. That's part of what slows down the airflow to eventually a normal shock inside the inlet. It expands a little bit, and then it gets to the front face of the compressor, the fan face of the compressor. Well, the F-16, and you can see it right here, has what we call a pitot inlet. It's basically a flat face air scoop. It is not that sort of overhang with a lip and then an inlet that's further back, like you see on the F4 or the F-15 or the F-14, the MiG-29, the Su-27. All of those have more of that inlet that's set up to put an oblique shock wave across the front of the inlet. Those are designed to go faster. The F-16 has a little bit of that. If you look at it on a side view, you can see how it's got a little bit of an overhang on the lip, and the nose helps to attach a shock wave. But it's not as efficient to go above Mach 1.2, and that's okay, actually. It can go that fast. It can go faster, but the engine is working a little bit harder as it gets into this 1.4, 1.5 Mach range compared to something like an F4 or an F-15. That's where they start to really stretch their legs and run.
These designs for optimizing maneuverability at these speeds can be seen elsewhere too. Its air intake placement underneath the aircraft, a stark difference to the side-mounted twin intake.
Yeah, so isn't F-16 like later designed from F-15, right? Or is that's not the case? I don't know. I'm pretty sure like somebody told me the F-16 was designed later on from F-15 and took a lot of things and design inspiration from F-15, and just like use the same engine F-15S but one rather than two. So I'm guessing F-15 was a response to the Fox battle with MiG-25, where they like assumed where's dogfighting going and not going, and they panicked because of the speed, but then later on realized like that wasn't for the dogfighting and things. And from them, I guess they're like, okay, you know what? It's like Mach 0.8 to 1.2, that's where dogfighting is going to be, because the Fox bat thing basically just proved to them that's not Soviets are going for or whatever, right? So they basically designed this for that. So they put that intake down deliberately, knowing that this is not made to go that faster, because they already have F-15. If they realize a situation requires high speed, they're going to just use F-15s. So this is specifically made for those low speed, for Mach 1 around speed things. It kind of makes sense, right? And they can tailor that from this to make it insanely agile.
Of the F4 and the thin, elongated wing that blends smoothly into the fuselage with these wing extensions forward of the main wing. These are called leading edge strakes. This air intake ensured the F-16's engine was not starved of air during high angle of attack maneuvers, with the forebody of the aircraft helping to funnel and divert air directly into the air intake. However, this does come with some problems that needed to be engineered around. On takeoff and landing, this air intake is only 100 centimeters off the ground. This, combined with the extremely thin wings, made placement of the landing gear difficult. The forward landing gear could not be mounted ahead of the air intake, as it would kick up debris into it, and they couldn't fit into the wings either, as the thin, aerodynamically optimized wing didn't have enough space. The F-16's landing gears are stored just behind the air intake, and in order to provide enough stability and bracing on landing, they need a unique folding mechanism to swing them outward to create as large a wheelbase as possible. The front landing gear, which is steerable during taxi, also rotates 90 degrees to lie flat just under the engine inlet. Above the inlet is a boundary layer diverter channel. This ensures the engine gets consistent laminar flow. As air travels along the length of the aircraft, it forms a layer of slow-moving, turbulent air called a boundary layer. If this air is allowed to enter the engine, it not only lowers performance, it can also damage the engine. As the turbine rotates, it will pass through the slow boundary air on one side and then the fast, free stream air on the other. This means the force on the turbine blades changes for each and every rotation, causing cyclical bending, a recipe for fatigue failure. This boundary layer diverter separates this layer and diverts it underneath the wings.
Can't you create this kind of like a cone type of like, what is it called, right? Like spiral wave type of vent thing that when the air basically comes from here, it can just spin in and mix it. I guess that you can kind of do that, but that would basically reduce the flow because nothing works better than the literal open intake. But I don't know, you have to make a really big, I guess it would work on a big planes, right? Like you can create that with a really big vent than you need and can have this kind of like a, spiral, I don't know what to call it, right? Spiral type of vent that basically mixes air rather than just like put air through raw or something, right? This metallic spiral thing that basically air takes it and just spins it and just basically mix it inside. I don't know. You could do that, but you need like a really big filter for it. Not filter, really big intake for it, which requires a really big plane, I guess.
All of this ensures the engine can operate as high a thrust as possible, even when the F-16 is performing extreme maneuvers, which is exactly when it is needed most, as the plane bleeds energy to produce lift. It's essential that a plane like this can continue to generate effective lift during these maneuvers. But typical wings lose lift as angle of attack increases beyond a certain angle, as flow separates from the wing. This is called a stall. These leading edge strakes help to mitigate that. They act similarly to the canards of the Su-34, one of the planes the F-16 will likely be going up against in Ukraine, with 19 of them reportedly being taken down thus far in the war. Canards and leading edge strakes help produce lift during high angle of attack maneuvers. Canards placed close to the wing, like the Saab 37 Viggen, create a vortex that passes over the wing, ensuring the wing continues to get high energy airflow during high angle of attack maneuvers, which allows it to continue generating lift. During the development of the F-16, General Dynamics did consider a canard configuration, testing different configurations and geometries, including versions with no strakes or canards, with subscale models in wind tunnels, testing through its optimum maneuvering speeds between 0.4 and 0.8 Mach. The goal was to maximize lift and minimize drag at high angles of attack, producing graphs like this, and these were used to compare designs. As they were narrowing down on the design, they consulted NASA, and they found one area to improve on: the sharpness of the leading edge. General Dynamics had rounded the leading edge of the wing to weaken these high angle of attack vortices, but NASA advised them to sharpen the leading edge in order to strengthen them. The F-16 underwent a great deal of iterative design in the wind tunnel phase before eventually landing on the design we are familiar with today, with the long blended leading edge strake that makes the F-16 immediately recognizable. And this comes with an added benefit. It provides enough space for the barrel of the F-16's powerful 20mm rotary cannon. You can see the barrel of the M61 Vulcan hiding here, a minor clue to the weapon hidden within the fuselage of the tiny plane.
Get out! Really? What the fuck? I didn't know that. That's a gun? Oh my god. I mean, yeah, it's a dogfighting. Why wouldn't I have a minigun there? Yeah. I've always seen things like this. Oh, look at that. They have like launch or something. No, apparently there was miniguns as well in there. Damn. It's one thing to have advantage like that, right? Like you have just NASA. You can just call NASA. Yeah, just in the name of defense, help us build this. And NASA's like, yeah, we have anything aerodynamic, we are literally leading of the world. We are NASA. That's what A is in NASA, right? So they are like, okay, we're gonna help, and yeah, there you go. Did NASA? I'm pretty sure NASA has helped in many other projects like F-35 as well, right? Why not?
To the weapon hidden within the fuselage of the tiny plane. One of the early conclusions of the Red Baron report was that the lackluster armament of the F-4 made it difficult for it to compete in close-quarter battles. It lacked an internal cannon, which left the F-4 without offensive options in close-quarter battles, where missiles could not be safely used. The F-4 was eventually retrofitted with the M61 slung underneath the plane. But the F-16, looking to fix the problems of the past, came with the General Dynamics M61 Vulcan rotary Gatling gun as standard. And it was packed neatly inside the plane, creating minimal aerodynamic drag. The M61 is the smaller cousin of the A-10's GA.
Oh, forget it.
U-8A, and while its rounds are tiny in comparison, the noise it emits still packs a punch. A massive cannon for a tiny aircraft.
Ooh!
The six-barrel cannon fires from the top position, spinning 16 times per second. The Gatling gun spews 120mm rounds per second. With an ammunition drum capable of holding just 511 rounds, the full ammunition drum can be unloaded in just over 5 seconds. The drum fits neatly behind the pilot here, and the vibration of the gun firing on the pilot's left side is jarring for
just 5 seconds? I mean, you can just hold the button just like one or twice and you're just empty of guns. Isn't that like really low? I don't know.
many new pilots.
It is such a small fighter. You know, when you, and I think I've said this before, when you get into an F-16, you sit down and you strap into that, it's not like you're sitting in the jet, it's like you're wearing the jet. And the gun is right here. As I sit there in the cockpit, the gun barrels, the muzzles are right back here. It's just out of reach. It's so close though. And so when you shoot the gun, and you're shooting 100 rounds a second of 20 millimeter, it is unbelievably violent in the jet, but you're thinking about the target that you have to go and shoot. And so, you know, one of my experiences flying the F-16 was I was teaching as an instructor pilot at Luke Air Force Base in Phoenix, Arizona. And so I had the privilege of taking in Air Force pilots. They're wearing wings, they've graduated Air Force pilot training, but they're not fighter pilots yet. And putting them into an F-16, and then we would make sure that everybody shot the gun in training. In fact, they had to qualify with the gun as a weapon. And so the first time experience for anybody shooting the gun in an F-16 is a little bit of an emotional experience. People would say funny things, they would cuss. It was all on the tapes, the HUD tapes, the heads-up display recordings. And we come back in the debrief and we kind of laugh at the students because they knew that they were going to go shoot the gun, and it was always shooting at a target on the ground is when they would do this for the first time, strafe. And so it's a little bit intense. You're diving at the ground, you're doing 450, 500 knots, pointed at the ground. Obviously, there's a survival instinct that kicks in there. You're trying to put the pipper on the target. You pull the trigger for the first time, and the whole jet shakes violently. It's like somebody started up a chainsaw just in your left ear. And the whole jet is shaking, and your hand's on the throttle there. And I can always remember every time I would shoot the gun, there's this hard foam insulation that's just behind the closeout panel. but the vibrations would cause some of those little bits of foam to flake off, and they would come around the closeout panel. And every time I would go shoot the gun for practice, for strafe, I'd come back, and as I'm getting out of the airplane, I'd see like these little yellow flecks of foam all over my green flight suit on my left arm. They would just, the vibrations were so intense. You get used to it after the first time you shoot it. It's a little bit of an emotional event, and after that, you're focused on, I need to put those rounds on target. So the F-16 is incredibly well integrated as far as a weapon system with that gun, and I will tell you that both for air-to-ground and also for air-to-air, the gun sights on the F-16 are incredibly precise, and even with dynamics on the aircraft, even under maneuvers in terms of air-to-air shoots where we're shooting at a banner. There's not been a lot of actual air-to-air dogfighting with the gun in recent memory, but the F-16 is incredibly accurate when it shoots at air-to-air practice targets, to the point of it's almost not even fair. It used to be kind of a scoring, kind of a skill thing, and now you can just park the pipper on the target, open up, and it just shreds anything you pointed at in terms of an air-to-air target. And then in terms of air-to-ground, you can be extremely precise with it. It's not quite a laser beam, but you can be extremely precise, and there's even ways that you can couple up other sensors on the aircraft and share information, even in a at-night, blacked out type of close air support role. You can hit what you want to hit on the ground.
All from a gun hidden away inside the tiny fighter.
Yeah.
If we follow this leading edge,
Okay, I don't get it. What does it mean, accurate? Like, does the gun swivel from inside just to hit the target? If not, wouldn't that be on the plane, like where you pointed it? How does it swivel from inside? That doesn't make sense. Like, wouldn't that? I don't know. So I'm guessing the electronics, when you aim at it, just like auto-corrects the trajectory without whatever you're doing, just to hit target with. I don't know. How is it accurate otherwise? Wouldn't you have to be accurate if it's just gonna hit where you point at it?
edge strake down the wing, we come to another device designed to increase lift at high angles of attack, the leading edge flap. It deflects downwards during high angle of attack maneuvers to delay stall, allowing air to remain attached to the wing surface. When performing a sustained turn at 0.9 Mach at cruising altitude, it increases lift by 18% and decreases drag by 22%. You can see them actuate here during the 5G takeoff I performed with the Thunderbirds back in 2019.
Okay.
The seam between the leading edge flap and the main wing is barely noticeable, and fitting a control system into this wing, which is only around 4 centimeters thick where the actuator system needed to fit, proved a challenge. The amount of torque needed to actuate a control surface like this at 0.9 Mach is not trivial. To solve this problem, power is transferred from 2 hydraulic motors, which convert the pressure in the hydraulic system into rotational motion. The hydraulic drive motor itself is tucked away behind the M61 rotary cannon, next to the hydraulic motor that drives the cannon's rotation and ammo drive system.
Okay.
This power has to be transferred to the wing, and this is done through a series of torque shafts, angular gearboxes, and down another series of torque shafts with rotary actuators in between. This
Okay.
leading edge flap is not controlled by the pilot, however. It's controlled automatically by the flight computer, and the F-16 was groundbreaking in this regard. The F-16 was the first fighter aircraft to have a fly-by-wire system controlling every control surface. The leading edge flaps, the flaperons, the rudder, and the horizontal tail of the F-16 are not controlled directly by the pilot. A fly-by-wire system uses a network of sensors, wires, and computers, as well as the pilot's own input to control the plane. The F-16 was employing this new technological wizardry to allow it to efficiently spend the energy its single jet engine provided.
Basically, if you have any modern cars, they would have fly-by-wire clutches. Basically having the same type of thing, but this being all the way back then, that would have been insanely new technology, right? I mean, I still remember driving a car that has like a hydraulic clutch, right? That literally gets controlled by the pedal you push it, right? And now fly-by-wire clutch, which is like there's literal difference, right? With the electronics and things, like car is doing things for you. You're just giving a suggestion in a way.
Traditional flight control systems up to this point used a mechanical system connected directly to the pilot's controls to manipulate the flight surfaces. This is footage of the F-4's control system. a heavy and complicated network of cables, rods, linkages, and hydraulics. It even has a 2-kilogram bob weight attached to the pilot's stick, a mechanism designed to make it harder to pull the stick as G's increase, an analog feedback system. To provide the pilot with analog feedback on speed, the F4 also featured a diaphragm that deflected with ram air taken from this probe on the vertical fin. This introduced a force that acted to push the stick backwards and indicated to the pilot to adjust a trim setting. This system not only added a huge amount of weight to the F4, reducing its maneuverability, it also added workload to the pilot and was more vulnerable to damage in dogfights with little redundancy. With a fly-by-wire system, none of this was needed. The first batch of F-16s actually had a stick that was immovable. It was just force sensing. Later, a small amount of movement was added after pilots complained.
So the non-movable stick, kind of little known fact, the original F-16, it wasn't a Lockheed Martin product, it was General Dynamics. And they had made the F-111 previously, and the weapon system operator on the F-111 had a small joystick that they could use to steer the attack radar. And that was a force-based movement. It wasn't really a joystick that would move, it was just the apply force. And so they took that same concept and then they put it into the F-16.
I can already feel how that would be fucked up. It's just like, that is like insane. Like imagine if somebody removes steering wheel from your car and put something like, let's just like this suggestive in that way. That would be fucked up. Like humans that rely on like the way we are basically, the way we feel things, and the way we are used to. All these pilots, I mean, obviously there's going to be new and there's going to be trained differently, but other pilots, experienced pilots, would have come from something like F4s or something. And imagine they're just being there and just like, okay, this stick doesn't really move. Changing feel like that is just weird.
16 stick. So it was sort of a General Dynamics thing of, we've got a force transducer, a control inceptor is what you'd call that. So what it turns out though is that the human body does really well with knowing where your limbs, hands are moving. Knowing the position of your body is something that you naturally do pretty well, and that is something called proprioceptive feedback. Well, when I have a force-based inceptor, I don't get that proprioceptive feedback anymore. And it's really hard to judge. It's something that I think if you challenge yourself to go pick up a small weight at the gym and ask yourself, how much does that weigh without looking at it? It's actually kind of hard to guess when you're down in those few pounds range. And the maximum force you can put on the F-16 side stick is 25 pounds. So it's kind of hard to tell the difference between 15 pounds and 15.2 pounds. We don't do very well with that. We do a lot better with knowing how far we've pulled something. And so the original F-16 controls didn't move, and what pilots found was that they were having a difficult time, the test pilots at Edwards were having a difficult time judging exactly how hard they would move the controls, and so they would think they were going to get a certain response from the jet, and then they weren't, and then they pull harder, too hard, and then they get a different response. There is a phenomenon called pilot-induced oscillations, or pilot-in-the-loop oscillations. Sometimes it's just shortened to PIO. And the F-16, even to this day, particularly if you have a lot of wing stores, can have a little bit of a wing rock on landing. And if you look at some videos of F-16s landing, sometimes you can find, if they have wing tanks or they're bringing back some bombs that they didn't expend, you'll find an F-16 that'll sort of do this little back and forth wing rock. And that is still to this day, it's an artifact of having a side stick that doesn't move very much, because it's one of those things that in terms of the mind to the hand, eye-hand coordination, you start to make a movement. By the time you see the effect, it's more than you wanted. So you take it out, you put in a correction. By the time the correction takes effect, it's more than you wanted. You see it, you come back. It's a feedback loop in our minds. And now, PIO is kind of a dirty word in aircraft design, and nobody wants any PIOs. I'll tell you, PIOs, pilot-induced oscillations, are like snakes. And some snakes are very dangerous, and some snakes are not. And so the PIO that's remaining in the F-16 in terms of its wing rock on final at landing is not super dangerous.
These pilot-induced
Wait a minute, so they didn't change it back? They didn't give them like, okay, the normal sticks, basically, they kept it, that one? Because, I thought like after complaining, they would have changed it or something. I mean, it makes sense, like everything we do, like there's a reason, like when we, I don't know, like climb stairs and things like that, we intuitively put our feet where it's supposed to be. When you really try to climb stairs and you really focus on it, like why you doing it, you'd feel like, oh wait a minute, I'm weird. And if anything, you will even like stumble and fall when you think too much. But when you're just doing it, you just do it, right? You don't control 100% of your mind in that way. There are some sections of part that is just like automated in a way, right? We just do it intuitively, right? That's why you don't control your heartbeat and things like that. So certain things are just intuitive. If you do it long enough time, it'll just be like a reflex, right? So things like that, I'm guessing that's also played a part, right? If you're stuck in that, you can just feel it, basically. Yeah, that makes sense. I guess, this was like one of those, I don't know if this applies to this or not. When I was a kid, I was playing a game. I always was, accustomed to mouse with. I was a big gamer when I was a kid. I always use mouse for everything. And then I had a laptop, and that laptop thing, right? It always felt weird to me. Like that never worked out for me because of this. Because I need a physical mouse that I can move, and it stops where I stop it or something. But yeah, same thing with the joystick. It doesn't work for me.
oscillations can also be naturally stabilized through passive stability, where the plane naturally self-corrects itself without pilot input. However, the F-16 was the first aircraft in history to do away with passive stability and make the plane intentionally unstable in flight. This was done because it lowers the energy needed to fly and maneuver.
We can understand why with this simple analogy. Here we have two situations, a ball placed on top of a hill and a ball placed in a valley. If we push the ball on top of the hill even a tiny bit, it will begin to accelerate down the hill and will not stop until we put energy in to slow it down. This is an unstable system. The opposite is true for the ball in the valley. Apply a force and the ball will roll uphill, and gravity will now provide a restoring force to bring it back. It may oscillate back and forth a few times before coming to a stop, but it will eventually return to its original position. This is a stable system. We want to tailor our stability to find a balance between these two scenarios, where we can cause a rapid change in direction with a small energy input, while also managing the amount of energy required to get back to our original position. This is called relaxed static stability. The F-16's pitch stability is one of the areas where this idea was applied. One of the key factors that affects pitch stability is the location of the center of gravity and center of lift. The center of gravity for the F4 is located about here. This is the point at which all lift will act around. It's like the fulcrum on a seesaw. As a result of the wing design, the center of lift is slightly behind the center of gravity. This would force the plane to pitch downwards, but the horizontal stabilizer provides a counteracting downwards force. This isn't ideal. We are wasting energy on downwards lift. We need upwards lift to fly. It also increases the amount of energy the F4 needs to input to change its pitch. When it pitches upwards, the force on the horizontal stabilizer decreases because of reduced airflow. And as a result, the weight of the plane, acting through the center of gravity, forward of the center of lift, wants to move the nose down again. But the pilot is trying to pitch the plane up, and this natural stability is fighting them. So, more kinetic energy has to be wasted by converting it to lift and drag with an increased elevator deflection. The F-16 is different. Its center of lift is ahead of its center of gravity, in part thanks to those leading edge strakes pushing the center of lift forward. This means to balance the plane, the horizontal stabilizer needs to create upwards lift. This is useful lift and reduces the energy needed to keep the plane airborne, and increases our maximum lift, pushing this line on our energy maneuverability diagram up, increasing our turn rate. However, it's an unstable system. When the plane pitches up, it increases the angle of attack on the wing and increases the lift. Because the center of lift is ahead of the center of gravity, this forces the nose up even more. In an air-to-air battle, energy isn't just a fuel-burning problem. Energy is needed to maneuver, and as we spend it, our ability to maneuver diminishes until we replenish it by gaining speed or altitude again.
Any fighter pilot will tell you, speed is life. And as a fighter pilot, energy management is one of the most important things that you can do. It's part of your situational awareness. in that combat arena. You don't want to get slow, and you don't want to put yourself in a place where you are vulnerable, and now I can't turn, I can't move, I can't get my sensors or my weapons engaged where I need to. And that's not just an air-to-air thing. That's in every aspect of being a fighter pilot. And that's even engaging in an air-to-ground arena, because oftentimes when you're engaging air-to-ground, an interdiction mission, a strike mission, or a close air support mission, well, you're supporting friendly troops on the ground, but there's also people that really don't like you in the vicinity, and they will have weapons also. And so you have to maintain that energy to be able to evade, to be able to move out of the way if you're getting shot at. And so with the energy...
Yeah, speed is energy technically, in physics-wise at least, right? The more fast you are, the more you energy have at that state. So it would make sense like how that would help maneuver you, right? The slow you are, that would be harder. Damn. As a fighter pilot, the more I watch things like this, I realize that the level of shit goes down that you need to remember this. I'm guessing in fight school, most of the things goes through just like you remembering stuff and just like feeling the thing, right? Getting shit right? I mean, yeah, this is also insane, right? Even small fuck up can be problematic, or you forget something. That could be problematic.
Energy management on the F-16, it's interesting that this jet doesn't really talk to you in terms of feedback to the pilot. It doesn't really shake and rattle and vibrate like a lot of other aircraft will do. I've flown the F-16, I've also flown the F-15, the F-18, the A-10, and those aircraft will talk to you, those other aircraft will talk to you a lot more than the F-16. The F-16 just feels smooth all the time, whether you're 200 knots and really slow or you're 600 knots and really fast. It just sort of does what you ask it to do. You think, you move the controls just a tiny bit, and the aircraft responds. So managing your energy becomes a situational awareness challenge for the fighter pilot. And so a lot of that's helped now with the Joint Helmet-Mounted Cueing System, or JHEMIX is what it's called, where right there in your right eye, you've got your airspeed, you've got your altitude, you've got your G, and so you can engage visually in that fight. I can keep my eyes on the threat, the target, keep situational awareness, and I don't have to look back in at my heads-up display or down at the console to see how fast I'm going and how high I'm going. You get the feel for it, you get a feel for how the aircraft is responding, but that's where experience comes in, and it's imperative, experience and training comes in. It's imperative to maintain that energy awareness in any kind of fight.
The unstable design of the F-16 helped fighter pilots like David to manage energy more efficiently. But to maintain control of an unstable fighter, a pilot would have to make constant, tiny corrections.
Yeah,
A
that's what I was
task
about to
deemed
say.
impossible before flight.
Yeah, when I heard it, that's what I was about to say. But yeah, okay, that's like useful in that way, but it's unstable for a reason. Like to get it like in control, especially during like really, hair-thin dogfights, basically, which you have to be in control every single, millisecond of those movements, right? You would need to know like what to do, how to basically correct things, right? So the F-16 is really great in a proper experienced pilot.
Fly-by-wire systems were invented. The system consists of a network of accelerometers, gyros, and airspeed sensors,
That makes sense.
all feeding into a central computer that manages the work. This instability makes the plane extremely nimble, ready to change direction with very little energy input.
Yeah.
We could see this in practice on the first flight of the F-16 prototype, the YF-16, a flight that was never supposed to happen. This was intended to be a short test along the runway, but the early control logic of the plane would not allow the engine nozzle to open to cut thrust if the wheels had left the ground, meaning even at idle, the plane was generating too much thrust. Then the plane rolled left, which caused the pilot to counteract it with a roll right command. But again, the control logic of the early prototype was not dialed in, with control input resulting in higher roll than expected at such a low speed, resulting in an overcorrection, leading to an oscillation. With this being the first full fly-by-wire plane, there were many lessons to be learned along the way.
But the benefits it now provides are game-changing. It helps the pilot get the most out of the plane.
So, for example, with an F-16, the airframe is limited to 9 Gs. And so I can go and pull back on the controls on an F-16, and if I am less than about 300 knots or so, actually more like 400 knots, I'm not gonna get 9 Gs. It's just, that's how much lift the aircraft can make. But once I get above about 400 to 450 knots, now That wing on the F-16 is capable of creating at least 9 Gs. In fact, it's capable of creating a lot more than 9 Gs. But what that fly-by-wire system does is when I start pulling back all the way to the stop, it goes to 9 Gs and it sits there. Even if the wing, even if the aerodynamic effect of the whole airframe is that it could generate 15 Gs or 20 Gs, the fly-by-wire system says, hey, I know you're asking for your best possible turn.
Yeah, I mean, 9 Gs, like, you're the limit. More than 9 Gs, I'm pretty sure human dies. I know there's like horizontal Gs and vertical Gs, a difference there. But yeah, 9 Gs post that is just like human is close to death, right? So 15 Gs would be catastrophic.
I'm just going to give you 9 Gs because we're not going to break the airplane. Or again, in like a slow speed fight where I'm having to, it's less than 300 knots, I'm having to crank the nose around to either bring my nose onto the adversary, or maybe I'm trying to jink out of the way of an adversary's weapon system. Pull suddenly on the controls of an aircraft and your angle of attack is going to increase rapidly. All right, well, with a lot of more conventional aircraft, you're worried about things like stall. Well, the F-16 doesn't really stall in the same kinds of ways, but that fly-by-wire system says, hey, I know that if you get past about 26 degrees angle of attack, bad things are going to start to happen in terms of the controllability. The F-16 stops behaving as predictably above 26 degrees angle of attack, and so the fly-by-wire system simply says, that's where I'm going to stop you right there, and I'm going to give you up to 26 degrees or 9 G.
What is...
And do with that whatever you need to.
A plane capable of 9G maneuvers is not much use if the pilot cannot remain conscious during them. The F-16 has some interesting adaptations in the cockpit for this. Traditionally, the control stick was mounted centrally, between the pilot's legs. This made it mechanically simpler, with the network of mechanical linkages being central and symmetric throughout the plane. It also allowed the pilots to use both hands to wrestle the control surfaces into position during high-G maneuvers, as the air flowing by them tried to...
All of that. Isn't like F-16 just one seat? How is it 2 seat? Or is it F-15 that's 1 seat? Wasn't F-16 just 1 seat? I didn't know you can have 2 there. I don't know.
pushed them back down. For the F-16, this wasn't a problem, and the control stick was mounted conveniently on the pilot's right-hand console. A comfortable resting position that makes it far easier for the pilot to control the plane while trying to stay conscious at 9 Gs. The seat is also reclined by 30 degrees. This makes the F-16 feel like an executive office in the sky, with unobstructed...
I'm like, just, sit there on your sofa, just like a joystick, like a PlayStation joystick in your hand. There you go. Now, if you can just make computers do most of the thing, I can just relax and play video game. But it's real life.
360-degree views thanks to the bubble canopy. But it also comes with major advantages in increasing the pilot's G tolerance.
Yeah. Okay, how much F-35 does this computer things, right? Because if computers can do most of the work, which obviously they can't in F-16 and things like that, they can manage somewhat, but obviously it's up to pilot. But the more advanced things get, I bet there will be a time where planes can do most of the work. You're just like, do this as point and shoot type of way.
The most common G-force a pilot experiences is directly down. When flying in a straight line, even cells in your body have inertia in that direction. And when suddenly pitching the plane upwards, those cells want to continue traveling in that direction. This isn't too much of a problem for cells that stay fixed, but your blood cells are free to travel through your body. And in a scenario like this, they race in the direction of that travel, pooling in your lower extremities. This can starve the pilot's brain of oxygen, and they can pass out as a result. This effect can be minimized by placing the pilot flat on their back. With the entire body aligned, blood wouldn't have to fight gravity to get to the brain. But this position isn't practical. The F-16 found a compromise with a 30-degree recline, reducing the pressure on the heart by an equivalent of about 1 G. The recline also makes it easier to fit taller pilots into the small forward fuselage of the F-16. Another measure to increase the pilot's G tolerance is the G-suit. A pilot's G-suit contains multiple air bladders that are connected directly to the F-16. When the plane is instructed to perform a high G maneuver, it immediately begins to pump compressed air into these bladders. This squeezes the pilot's legs to limit the volume available for blood to pool into. The F-16 is a 45-year-old aircraft, and many advances have occurred in aviation since its maiden flight. Stealth technology and interconnected intelligence networks have been the main focus for fifth-generation aircraft like the F-35 that have been slowly replacing the F-16. But one thing has not changed since 1975: physics. The F-16 pushes the boundaries of maneuverability for a fighter aircraft and the pilot inside. It's a highly capable fighter aircraft that the strongest air force in the world deemed capable of continuing service until 2048. The plane will be a major asset in the next phase of the fight.
I mean, you can do tweaks here, you can add technology, you can do all the stealth crap, but in the end, physics is physics. And if something works, it fucking works. And if they reach the limit of maneuverability using physics back then, they're not going to make that much of improvement today, will they? And especially for what it does, right? You can make another plane that specified range does something well. I'm guessing F-22 is best because I'm pretty sure it has like a higher speed than this, right? 1.5 or something like, it can do it. But this is mostly made for 0.8 to 1.2. It can do more, but that's where it's supposed to do its thing. F-22 does it more higher range. I don't know. I remember saying that this is the best dogfighting plane, F-22. So I guess it does something better. But yeah, I guess physics is not going to change. So yeah, but that's a long time, 2048 or something, damn.
For Ukraine's freedom, providing essential air support to the troops on the ground as they attempt to push forward through entrenched Russian defenses. Ukraine has been targeting long-range anti-aircraft batteries with success and captured oil platforms off the coast of Crimea that were housing Russian sensors, all to clear the way for Ukrainian Su-24s to get close enough to launch cruise missiles, targeting high-value Russian assets in Crimea, including a Kilo-class submarine. The F-16 can also carry these cruise missiles. Every asset in the Ukrainian Air Force is going to play a vital role in Ukraine's fight for freedom. Having an actual fighter pilot add context to this story was incredibly valuable, helping us truly understand the power of those energy maneuverability diagrams. We ended up talking to David for nearly 2 hours and ended up cutting an incredibly interesting story from this video about how he helped develop an automatic obstacle avoidance system for the F-16 that has saved many lives. A fascinating system that works in a way I didn't expect. I had assumed it simply used radar to measure distance, but that is not how it works. You can watch that extra video on Nebula right now, along with...
Yeah, we'll go to nebula.tv / real engineering and support this channel. Yeah, that was good. Like, he got an actual engineer, actual fighter pilot, basically. That was a good thing. I guess when you reach 4 million subscribers, you can get certain perks. Like, you can get people, I guess. That was a good thing. I like the inclusion of that. That made this video really good. Yeah, F-16 is insanely good. Didn't realize this. I just thought it's just F-15, one engine remove. But no, it's very, very different. Damn. I like how all these like F planes have their own places, right? It's not like, one is better or anything. They're better in their own thing. F-35 is supposed to like replace F-16, but isn't F-35 has that its own thing? I mean, if prime F-16 scenarios, F-35 wouldn't work, I think, right? F-35 is made in a different way. Like, it's made to basically communicate with each other, right? It's made in a way they can attack things from the distance because it's that accurate, right? But is it just like, let's just say from like anywhere around 1 Mach, can it do the same type of maneuver and things like that? Is it that level of agile? I don't know. Everything has its own place, I guess, right? And even if you have like F-35, F-16s, and even F-22, I guess that's the whole job of a general or commander, whatever, to know the situation and from there on make a decision who should go and what should do, right? That's the whole thing. A good general can change everything, right, with the equipment you have. Well, that was the insane engineering of the F-16, the channel Real Engineering. If you like my reaction, don't forget to subscribe. There are other videos I've done from this channel, F-35 and things like that. If you haven't seen them, check out the link in the description or check out the end card right now. And yeah, don't forget to subscribe. That way you can be up to date when I post videos like this. I try to post videos like this every day. But yeah, all right, I'll see you next time.